Welcome to the 2023 NORR program. I'm Silvio Baldessera, Chair Emeritus of NORR, founder of NORR, and your host. NORR is a continuing education program founded 16 years ago with three main goals: to teach, learn, improve, and to do that continuously. The program relies on bringing the best speakers in three series: architecture, engineering, and the masters. Each of the NORR virtual sessions since 2020 have been recorded and are available on NORR YouTube for global access. Welcome to the 14 NORR office staff and invited guests. Welcome to the students of the 16 schools of architecture from Canada, the US, and the UK, as well as Europe. In Milan, Italy, Stefano Boeri Architects envisions the leading developer's vertical forest, a healthy, comfortable, inspirational indoors and outdoors high-rise residential tower in the heart of the city, a home for the future, a response to not only the EU carbon roadmap, but to the G7 and the UN net zero targets towards trying to meet 2030 and 2050. This is a future response that addresses the challenge. And for those of you who live in a high-rise residential, is this even an option to the developments in your cities available to you? Our speaker today, Thomas Auer, is partner of Transsolar Stuttgart. The climate engineering practice has received international attention over the last 3 decades and is working on all scales, from single buildings to urban neighborhoods. As professor and chair of building technology and climate responsive design at the Department of Architecture of TU Munich, focuses on holistic design approach. From buildings and cities, it is crucial to recognize the sustainability goals of the EU, as well as the reduction of substantial CO2 emissions in the building sector as defining parameters. Thomas and Transsolar have always advocated an understanding of the energy efficiency that goes beyond technology. They develop holistic concepts that incorporate the urban and regional scale. The overall objective of this approach is to create maximum comfort in the interior as well as in the exterior of the building environment while minimizing the use of resources at the same time. Thomas works in interdisciplinary teams and has established a 3-step approach comprising space design, building performance design, and infrastructure design. Welcome today to Thomas Auer, and who will be presenting Lost in Transformation. Thomas.
Silvio, thank you very much. Thank you very much for the kind introduction, but also thank you very much for the invitation. I think it's a great pleasure for me to be part of this series, being part of these amazing speakers you invited for this educational series. So today, my lecture will be a bit of a critical reflection, let's say, of our work. Not that I want to criticize our work, not at all, but also critical reflection of what we are doing as an industry. So let me start with my presentation. So this is obviously what we need to aim for. The building stock has to become carbon neutral based on the EU legislation. We have to be carbon neutral by 2045. However, at the same time, we know certain strategies, but do we have all answers? I think that's something we certainly need to question. And this requirement is certainly gonna change our built environment. And to that regard, it's so essential that we design this transformation and that it's not just going to happen. If we look back in architecture history, this is what you see is downtown Manhattan in the early 20th century. You see the Flatiron Building, and you can see that on every single window, there's an external shading device. Every single window is operable for natural ventilation. And there is a very simple reason for that, because Carrier invented the air conditioning in the 20s. So none of these buildings had air conditioning at the time, and designers knew how to make the best out of the situation, how to provide reasonable comfort. I don't want to say it was always super comfortable. We all know that New York, as well as Toronto, can become unbearable in summer, but it was the best they could do with passive means. And then through the periods of modernism and the invention of the curtain wall, the glass curtain wall, the invention of air conditioning, suddenly we see buildings like this glass tower in the center, which became kind of international style, no operable windows, let's say deep floor plates. Most people disconnect them from the facade, no daylight. And even those who are sitting on the facade, there's so much coating on this glass that the daylight doesn't even have the same color as outdoors. So if you look through such a glass panel, the grass you can see outside, if there would be grass, would not have the same green than being outside. So if there is a power failure in Manhattan, people have to leave that building. Whereas in the Flatiron Building built 80 years earlier, you can open a window for natural ventilation. So what did we miss on this path? And then when we started Transsolar in the early 90s, we really believed in the fact that we can bring transparency, that we can bring means of passive operation integrated into this modern international style architecture. And as a result, certainly one of the most important building I worked in my career, the Manitoba Hydro Building, for instance, in Winnipeg, where we worked with KPMB architects from Toronto. John Peterson was project architect, also joining, or project manager, also joining this call today. We worked on a lengthy schematic design process. It was almost research with the objective to design the most energy efficient high-rise building in North America. Winnipeg, you all know, has a harsh climate. I don't want to go into the details. We did a long study on climate conditions, analyzing climate. It can become very cold with temperatures going down to minus 35 degrees C, which is about the same in Fahrenheit at that low temperatures. However, what you see here is very typical. Whenever it's really cold, it tends to be always sunny. And so we studied how much solar radiation we have in Winnipeg, and we found that Winnipeg has almost as much solar radiation as Rome, much more than any city in Germany, more than the city of Milan in Italy. And actually, we also studied how much solar radiation do we get on a vertical south facade. It was more in winter than in summer. So this became the driver. How can we maximize the use of passive solar energy in building operation? So we ended up with a kind of a twin tower with two high-rise bars, one facing east, one facing west. The shape has been given by the site by various parameters, but due to this kind of V shape of these two towers, there is a kind of a leftover space, which we called the winter garden. So in a section, so this is how we operate the building in winter. We have an 18-story tower on a 3-story podium. And we have divided the 18-story tower in what we call 6-story neighborhoods. And so we have 3 6-story winter gardens. And so we get in winter, we get outside air into the winter garden and condition this outside air to 10 degrees C to 50 Fahrenheit. So we condition this winter garden in winter only to 10 degrees C, so that when the sun comes out, the sun further heats up the air, which we then, heated by the sun, distribute into the depth of the floor plate. We have radiant heating in the north side. We have a chimney where we take the air into the basement, where we have a heat recovery system. I don't want to go into the details. And we have almost 300 boreholes, geothermal boreholes under the building. With the heat pump, we provide 50% of the heating demand through our radiant system, which is embedded in the concrete slab. So we have a 30 centimeter, 1 foot thick slab with tubing, hydronic tubing embedded in the core of the slab to provide radiant heating. And in summer, when we don't need heat recovery anymore, we use this chimney as a solar chimney to drive natural ventilation, to exhaust naturally. We use the geothermal system for cooling purposes, run cold water through the slab. We open this southern facade so that we get basically outdoor conditions in those winter gardens. So that's the whole strategy. So it's pretty straightforward. And this is the winter garden. This is basically the mechanical room of the building. There is no, for the office spaces, there is no other mechanical room for mechanical ventilation for air handling units. The supply air units are integrated into this bench you see on the bottom right. And behind the panels you see on the left side are the units that take the air from the winter garden and distribute it by a raised floor planning. And then we have a water feature in the background, which provides humidification. To the east and to the west, we do get climate control by a double facade. The double facade has the insulating layer on the outside, the single glazed layer on the inside, a Venetian shading device in the facade corridor. But we do have, because of the double facade, we could manage to have operable windows for natural ventilation. We also, I think it has big advantages in terms of building physics. I don't want to go into the details, but let me say one thing. It's just in such a cold climate, it's just not true that we are able to manage a temperature difference from 20 degrees outside, from minus 35 degrees or minus 30 degrees outside to plus 20 inside in a thickness of something like 4 inches of a glass facade. So you always have cold bridges, you always get condensation, you always get mold growth in those kind of single glazed facade systems. Not single glass, but single facade systems. So because of the depth of the facade, we could deal also with these building physics issues. And so what does it mean? So what we are very proud of is that all workstations are exposed to daylight, are exposed to natural ventilation. Manitoba Hydro has measured 1.25 less sick days in this building compared to their other facilities. And they have monitored already in the 3rd year of operation that they do get half as many calls for too hot or too cold compared to their other facilities. And this is very interesting. Now we can certainly, let's say, have discussions about why, but it's all speculation. We don't really know why. But it's interesting because we provide heating and cooling, not with the ventilation system. All year long, we supply air at 18 degrees C, and we heat and cool the space by the radiant system, which is embedded in a 1 foot thick slab. So it's so slow reacting that if someone complains about high temperatures, it would take a day or 2 to correct the temperature by 1 or 2 degrees. So it's so slow reacting that there is basically no possibility to interfere. Whereas the other buildings are fully air conditioned, and there's a thermostat where people can say, now it's so hot, and reduce temperature down to 24, and then an air conditioner kicks in. So that's very interesting, despite the fact that we have basically no control, and especially no individual control, we have half as many complaints about too hot or too cold. In terms of energy, you see MNECB, which was the energy code at the time, 258 kilowatt hours per square meter and year. And our modeling in design, our projection showed 88 kilowatt hours per square meter and year. So this is when we started construction. And then after completion, after final completion, kind of final completion, you know, this problem that people move in a building and it's not really finished. But anyway, when they moved into this building, we monitored the building over a period of 2 years. And you see here the results. We measured the energy numbers in September 2010 and then in October 2010, always looking at the previous year. And the green line are the 88 kilowatt hours of our simulation model. You see at the first year of full set of data in September 2010, we had what we call performance gap of almost 100%. So the building used almost twice as much energy as what we have predicted. And then it took us the full 2 years to get the building to operate as designed, a period of 2 years. We had one hydronic issue, which had several reasons. Everything else was like a bucket list of whatever, 100 or more small things. And you have to find them. You really have to dig deep into the systems, like a sensor that measures the wrong temperature, a routine which is just not correct, a sensor which is not connected, a valve which doesn't close, etc., etc. You need to find those, and it took us 2 years. So that was kind of frustrating. Why did it take 2 years? First of all, we were certainly proud to get the building to work as designed. And in general, we are very proud of this building. I have to say this. It's certainly one of the most important projects of Transsolar. It's certainly one, if not the most important project for me. And it's a very successful project. And the question I raise is, why does it take so long? And then we digged at the university, we digged into this issue of performance gap, asking whether it's an issue of a Transsolar building, are our buildings too complicated, or is it a general issue of the industry? We found several studies from Germany, from England, tons of studies in the US. And this study, for instance, from the Royal Institute of British Architects, which is called Better Spaces for Learning, they looked into almost 60,000 school buildings all over Europe and found that 95% do not work as designed. 95%. So we have to, let's say, conclude we have a big quality control issue in our industry. We have a big issue with performance gap. We have a big issue with all kinds of things. Now, what do? How do we solve this? So the question is this a role model? Are the buildings too complicated? Again, the client, Manitoba Hydro, is very happy with this building. We are extremely happy with this building. Everybody is very happy with this building. However, is it a good role model? We always believed that through what we call adaptive facades, climate responsive design, however you want to call it, we can, let's say, create transparency in a very smart way, so that we reach efficiency, a higher level of efficiency. And now we need to question whether, let's say, the buildings are too complicated, whether this maximizing efficiency is an appropriate and the right approach and goal. And then the other thing that is really frustrating, almost nobody in North America, even though Manitoba Hydro is considered a success, And everybody who wants to do an ambitious, sustainable building in North America, everybody knows, but almost nobody on a bigger scale tried to copy this idea of a climate responsive building. What we see, this is not North America, this is London, this is Canary Wharf. What we see is worldwide single glass buildings, no opera windows, no shading device, no nothing of what we try to integrate in the Manitoba Hydro building and others. And let me be blunt, these are all stupid glass buildings. And what now, since in Europe we have ESG, so all these banks sitting in those towers need to do sustainable reporting. About a year ago, I heard someone from Europe giving a talk about those buildings. And he said it's considered a big problem because now suddenly all these banks, through their sustainability reporting, recognize that those buildings are energy eaters. And they try to find solutions and they have no idea how to fix it. So we built a building stock, something like 30-ish years ago, which is already outdated, which is already a dinosaur. And so we have to conclude that we can't do this anymore. We shouldn't do this anymore. We have to become smarter with what we do, and we have to think about our role models. And the question we ask ourselves, so first of all, the critical reflection, is that we have to conclude that this glass and high-tech architecture has failed as a role model in terms of sustainability. Again, not the individual buildings failed. It's a super successful building, Manitoba Hydro, I'm very proud of, but it never made it as a role model. So we need better and smarter role models. And it's for sure the role models have to be easier. They have to be more simple. And then the question we can ask ourselves, does the past become the new role model? So can we learn from the past? And then we did a study, unfortunately in German, which got published in a book where we looked at 12 school buildings. And I want to go very short. It's a very thick book, but I want to just highlight one building, which is on the top left. It's a building from 1898, designed by Theodor Fischer, who was a very important architect at that time in Munich and Stuttgart in the south of Germany. And here you see pictures from the classrooms, and you already recognize that this classroom is more spacey. And so they had 800 square feet as a classroom instead of something like 500-ish. We design classrooms today. They had let me calculate, 13, almost 14 feet tall floor to ceiling height, instead of something like 10, what we do today. So the space, the air volume per person inside the space is about twice of what we design today. In addition, they have thick walls. Here you see a section. They have thick brick walls, something like 60 centimeter, 40 centimeter thick brick partition walls. Sorry if I sometimes use international metrics, standard international, that's how it's called, and sometimes imperial metrics. I'm sorry for that. I hope you can calculate, you can do the translation in your head. So thick brick walls. And so the result was, it's still not common that we mechanically ventilate and air condition and cool school buildings in Germany in our very moderate climate, where over the summer school is closed over a period of 6 weeks. So saying that, in all buildings without mechanical cooling, we measure the best comfort in this building in summer. Of all buildings without mechanical ventilation, we measure the best air quality in this building. With the smallest fenestration ratio, we have the best and most evenly distributed daylight due to these tall windows and the tall space. So we recognize that height matters. Height matters in terms of air quality, height matters in terms of daylight, but height matters also in terms of thermal mass of these coming from these walls being exposed to the space. That was quite interesting. And that was also in a way shocking that a 120 years old building outperformed basically all the others. And then in terms of energy, the difference to the most innovative, most efficient buildings is something like 30%. 30%, which is the difference of changing from blackboards to whiteboards. The power demand for the whiteboards is about the same than the 30% in energy performance, a difference in energy performance. But if we look at the mechanical rooms, then in the Theodor Fischer building, we have a boiler room which has something like 300 square feet, whereas in the most innovative building, highest energy efficiency on the bottom right, in Diedorf, we have the architects, they needed to build a gym under the building to house all these, let's say, energy efficiency, mechanical ventilation equipment. The facility manager is sitting in a cockpit behind a bunch of monitors controlling a school. It's a school. So it was a research project. There was an institute involved. It took them 3 years to get the building to operate as designed. The Theodor Fischer building, the upper left building, got now renovated the first time. So after 120 years, it got the first time through a major renovation. Nobody of us believes that the system on the bottom right is still working as designed in 10 or 20 years from now. So this is not robust. So what do we do? And then my colleague at TUM, Florian Nagler, a very known architect in Germany, he said, Thomas, let's start a research project. There were many, there was not just him and me. There were like many companies, institutes from the university involved. And we called it Einfach bauen, build simple. How can we reduce complexity in design? And we said, let's focus on 3 materials, and maybe let's start with comparing space and materials. But we also said, like, we want to build monolithic again. We want to reduce layers. We don't want to glue insulation onto a concrete wall. No composites of materials, just single materials, which we can then bring also back into the cycle. So the whole idea of circularity was included, but particularly reducing everything we don't really need. And then there was this question. So Florian and his chair, they were looking into sections saying, if we build a facade nowadays in Europe out of concrete, we have a load-bearing concrete wall, and we glue insulation onto it. No real solutions, again, how to separate it later on at the end of life. Then we have a shading device. Because of the shading device, we create a cold bridge. If we really want to fix this cold bridge, we use a vacuum insulation panel. Nobody knows how long the vacuum is going to last. And then what's very typical in Germany, not so typical in North America, on the inside, we have a concrete slab. And on top of the concrete slab, we have like a 2-inch insulation and a 2-inch concrete screed, like a floating screed on top of it. And we do this for acoustic reasons. But if we're honest, the main reason is that we run all the surfaces, all the piping, all the electrical wiring, we run in this, below this screed, in this insulation layer, just to hide it. And so he did the same for timber. He did the same for insulating brick. And then we did studies on looking on spatial, optimizing space, let's say. So we did studies looking on 81 geometries. So what's the best ratio between width and depth and also height, knowing that if you go taller, the window becomes taller, and then you have daylight going deeper into your space. So with less glass, you achieve better daylight, more evenly distributed daylight. So we ended up with 81 geometries and 4 orientations and 3 different building materials and 3 different glass types. So with almost 3,000 versions, we modeled to find an optimum. And then we were also, as a team, going through a life cycle analysis. I think I jump over this because I don't want to go too much into the details. And then there was a developer, the B&O group, Dr. Böhm, nearby Munich. He was so excited about this idea of simplifying construction. He was so excited about our research that he built us 3 buildings. So Florian Nagler, he has an architecture firm. He designed the 3 buildings, one out of insulating concrete, one out of mass timber, and one out of insulating brick. And as you can already see, we said no composite of materials. So you see the bricklayer trying to, let's say, create this arch on top of the window. And the reason is very simple. We didn't want to have a concrete beam on top of the window because the concrete beam would be a cold bridge. Then we would need to glue insulation on it and so on. We wanted to avoid all of this. So we said no mix of materials. Everything remains pure. And so therefore also the concrete, there was no reinforcement in the concrete. And therefore also you can't get a beam if you don't have steel in your concrete. So it's not reinforced insulating concrete, this wall, and therefore you also see these arch type windows. Here the proof that there is, when they poured this insulating concrete, that there was no reinforcement in this formwork. As a result, if you don't hide the installation, the electrical wiring and the piping under your screed, everything becomes exposed. But that became a whole theory, at least here in Europe, but also I think in North America, everything I heard. And in Switzerland, they say all system needs to be accessible. The expected lifetime of these pipes for this radiator is something like 40 years. The expected lifetime of a building is 100 years. So you need to replace the piping within the lifetime of the building, and therefore it has to be accessible. If it's below a screed, you have to rip out the screed to get to your piping. The same with the electrical wiring, the same with all the systems. And then we designed this for a height of almost 10.5 foot. You see, we have a fenestration ratio of less than 20%. We have these tall windows because of this reduced fenestration ratio of less than 20%. We could avoid the need of shading devices. And you see how good the daylight is in these buildings. We used only natural material. It's a seesaw we put on the floor, which we needed for the acoustics. We needed because we didn't have a screed. We didn't put in a screed. Therefore, we needed to have a soft floor finish. Again, those are the 3 buildings. And then we had 3 PhD, or we do have 3 PhD students doing their PhD on these buildings. We did measurements over a period of 2 years, and we received some very interesting results. Here you see some measurement equipment we put into those buildings. And if I look at comfort, this is the European, or the German, I have to say, the German comfort zone. So each dot is representing one measurement during occupation time. That's very important. So we always measured noise. If we had no noise, we knew that the space is not occupied, and we took only the occupied time. And then on the horizontal axis, you have the outdoor temperature. On the vertical axis, you have the indoor temperature, and the gray band is indicating the German comfort band. And you see that people accept lower temperatures in winter, which is quite interesting. And we saw this in all buildings. The lowest we saw in the timber building. Of course, the radiators and the heating system is designed for providing 20 degrees. So obviously it was a user choice to have lower temperatures than 20 degrees during occupation time, and it's a living room. And then what was also interesting is that you see here what we would call overheating based on this comfort zone. but it's mainly at outdoor temperatures below 20 degrees, so people could open their window, creating some cross ventilation to get rid of this overheating. So obviously, it's also a user preference. And we don't see overheating when it gets really hot outside. So at temperatures outside, let's say above, what do we have here, 27 degrees, we are within the comfort band. If we use the adaptive comfort standards based on the European code, which you also have in ASHRAE, suddenly we see that in summer, we are even below category 1. So what we would call the best comfort. So that's very interesting. You see how different the different codes are. And we use this now to argue in Germany with the central government that for all public buildings, we have to use European code and not this German code. In terms of energy, we measured 2 apartments in each building in depth, in detail, and you see the heating demand of those 6 apartments. Now it's, let's say, statistically a very low amount of apartments, of users. But anyway, it's certainly an indication. What you see on the horizontal axis is what we have projected in design, the energy consumption, and on the left, on the vertical axis, what we measured. And so everything which would be on the 45-degree line is exactly where measurement hits the projection. Everything which is above, we would have a performance gap. Everything which is below, we basically have a negative performance gap. And this is quite interesting. In 5 out of 6 apartments, and this was before the energy crisis as a result of the Ukraine war, this was the winter before, we have a negative performance gap, even though we designed those 3 buildings towards the minimum energy requirements based on code. So we said we don't do anything beyond that. Just what we have, what we are mandatory to do. But the buildings use less energy. And then there was interesting, there's a passive house district, so highest energy efficient standards in Wiesbaden, and they published their measured energy numbers. And you see that in this solid, in this mass timber building, the energy consumption is even lower, or let's say plus minus the same as the passive house. So we really question whether efficiency will get us anywhere. Is efficiency really a solution? We measured also the ventilation, how do people ventilate, etc., and then recognized that their ventilation strategy is very reasonable. And then there's also a sociologist involved, and we had questionnaires. We asked people, and they all say the space is so airy, so spacey, that the air quality, they have the feeling the air quality is always good, so that they don't have the feeling that they constantly need to open the window. And in combination with the low temperatures, this is the effect. So the effect is that we don't see a performance gap. It's actually the opposite. But it was never designed towards efficiency. Also in terms of space, we gave them more height. So again, you see here those 3 buildings. So it's not hundreds of users, it's not thousands of users, but it's certainly an indication. So what are potential role models then if efficiency is not the only one? And if we say we have to get beyond the glass architecture, that's something I think we can certainly conclude. And embodied carbon became more and more important. And of course, we have to take embodied carbon into account. Let me show you a couple of projects which goes into the right direction, which might give us an indication. I'm not sure if you have the answer, but the simplicity, this Einfachbauen, is certainly something that guides into the right direction. But when we wanted to translate this in a dense urban environment, we had big issues because of the thick walls and square meters of floor area we lose, big issues because of zoning bylaws and extended floor to ceiling heights. Then this is this super high efficient timber school I mentioned from Florian Nagler, my colleague, to which he designed together with another colleague of us, Hermann Kaufmann, as a zero energy school, where they have these huge mechanical systems to provide the energy efficiency. And we concluded that those complex systems will never lead us to the energy numbers, to the decarbonization we really need. Because who is going to maintain those systems? Who is going to fix? Who is going to design and build those systems? Just if we translate the 50,000 schools we have in Germany and the manpower we would need if this is the model, we see it's not going to work. This can't be the model. So then we used this Einfach bauen and translated it into an office building for Alnatura with Haas Cook Zemmerich architects here from Stuttgart. And we used rammed earth material, a local material, a natural material, low, almost zero embodied carbon from the site, and or let's say almost from the site. And we measured. It's pretty thick, was almost 2.5 foot thick, and we could show how passively the walls controlled temperature and humidity in this building. However, again, thick walls, can you translate it into an urban environment? Zoning bylaws, losing too much space, etc., etc. It's also, let's say, very labor intense. So is rammed earth really the future? And then this is a building we haven't been involved from in situ, really nice building where they used 95% of all materials are reused in this extension of this old manufacturing hall. 95% and reuse of materials or reclaimed materials, however you want to call it, is certainly a hot topic, very important topic. We have to take more into account. However, in Germany in 2019, we built 150,000 new buildings, whereas we tiered down 15,000 buildings. There's a study in Germany that if we reclaim all materials from demolished buildings and bring it back into the cycle, we can, let's say, with the construction we have today, we can cover something like 10%. So it also contributes, but is it the solution? Then we see, I mean, Silvio showed the Boeri building in Milan, this greening facades. This is the WOHA building in Singapore. We took an infrared image from, and you see how this green cools. You see how the green cools in public realm. You see how the green cools on these terraces of this hotel. But you see also how these glass facades heat up and basically destroy all the cooling effect from the green. So we really need to question. I mean, I love the Boeri building, and it's certainly a message, but we really need to question whether we can replace the function of green in public realm by green we put into the facades. Green belongs into the ground, and the public realm and the facade green does provide cooling, but it doesn't provide shading, whereas a tree provides cooling and shade, and we need to provide shade in public realm. And then finally, let me finish with comfort, talking about comfort. So, I mean, all these approaches I have shown you are not providing us the answer. But I think all the approaches are important and valid, that we continue trying to find, let's say, or to rethink an architectural approach that is truly sustainable for the future. Like, we need a new type of international style, which is based on local materials, and a new type of international also aesthetic, which is based on local materials, reused materials, bio-based materials. All of this we have to let's say, integrate into our architectural approach. It's not one single answer. This is what we know for sure. I don't have the answer. I don't have the project where I say this is the future. But I think all aspects we have to consider, and I'm convinced there will not be one answer. But one thing I'm very convinced of is that we have to rethink comfort. And we are doing research about this also at the university. We started something we call Sense Lab. So it's a box where we can provide all kinds of conditions and then put test subjects, like we do studies mainly with students, I have to say. But we put test subjects into those rooms and use biosignals to try to find, let's say, a correlation between conditions and well-being and health. So that's a little bit what we aim for. So we use all kinds of biosignals. This is the Sense Lab, this is the space. And let's say in the old thermal comfort research and all the Fanger, all the ASHRAE standards, the usual ASHRAE standards, not the adaptive comfort standards, but the regular ASHRAE standards are based on this research, which always use questionnaires. So they put people in a test chamber at stable conditions, no change of conditions. And then after a while, they came out, said like, how did I feel? And so this was used to find how people perceive comfort. I mean, that's the point. How do we perceive comfort? But you can't have changing conditions. So that's why we ended up with a very narrow comfort band. And we ended up with the narrative of very stable conditions throughout the day, throughout the year. And our hypothesis is that more dynamic, changing conditions is actually more healthy for people. And we let people stay there for 8 hours a day, which also almost nobody did before. So it was always like a short-term stay until you get to steady state conditions. And then you were going through the questionnaire. And what was very interesting, so we put test subjects or we let people work in this test box for 8 hours a day at 25. This was one of the first studies we did already something like 2 years ago. At 25, 27, 28, 29, 30 degrees. So 30 degrees is something like 90-ish, a bit more than 90 Fahrenheit. And it was quite interesting. We measured their electrical conductivity of their skin so that we can see when they sweat before they even recognize they're sweating. So that we see when they build up heat stress. And you see that in the morning, like at this number one test subject, for instance, in the morning, in the first 4 hours of work before the break, things are quite fine, quite okay. Here it creates some heat stress, but it's very horizontal, it's very flat, and it's quite okay. And this is let's say, a pattern we saw with all the test subjects. Very independent from the temperature. Everybody was fine in the morning, and then built up heat stress in the afternoon, after lunch, after digestion, when the biorhythm, we found out the circadian cycle is not just related to light color, it's also related to the body temperature. In the circadian light cycle, in the circadian cycle shows also that the body temperature is going up over the course of the day, and it's about the highest at 6 p.m. in the afternoon. And you see the test subject number 3, and you can clearly see that at this day he might have had a hangover. But there was a very coming back to all the people we tested, there was a very clear pattern. And this pattern we saw in all new studies we did, that people are quite fine, almost independent of temperature in the morning. But then in the afternoon, we see heat stress, almost also independent of temperature, but we see that at 27 degrees in the afternoon, it's getting more. So this was quite interesting. So we ask ourselves questions. Like, for instance, a simple question would be, are people designed for working 8 hours per day? Or the next question would be, was siesta maybe a good idea in summer? Could the body get a reset by having a longer break? And these are all things we studied this summer, but we're going through all the numbers we created so far. So we still need to analyze all the results. But those are the kind of things we do. But however, I'm very convinced, absolutely convinced that thermal comfort has no correlation to health. And there are studies, one study being done in Montreal about low temperature, showing that if you expose people to low temperatures, they're getting used to it, they're more healthy. There's another study have been done in Belgium where they exposed people to high temperatures, to almost 95 degrees, let them work over weeks, a month, and found that they lowered their risk of getting diabetes. So I'm totally convinced that putting the body into stress out of the comfort zone every once in a while is actually healthy. Changing conditions over the course of the day, dynamic comfort, what we call it, is actually aspirational for people and maybe even healthy. So it's still in a stage of hypothesis. We have to prove it. But if we prove it, I think we end up with different building designs. And then let's say, let me finish with this quote from Daniel Barber. He wrote this amazing essay, which is called After Comfort. And just a few quotes out of his essay. He said, "Comfort, like capital, is unevenly distributed. So we always always take comfort for granted and forget that it's a very small percentage of the people on this planet do have access to comfort, to have access to heating and air conditioning." And then he says, "Comfort, however, is in short supply. In the face of the climate crisis, we have to collectively adjust to its going away." And then he says, "Architects are on the front lines. Finally, the avant-garde, building a world at the edge of discomfort to express and build non-carbon possibilities to explore life after comfort." Thank you very much.
Thomas, thank you. It's for sharing that very inspirational. I mean, you know, the research that you've done and new way of looking at what we as architects and engineers that are on this talk should be really focusing on. And certainly the three buildings that you showed were quite inspirational. And thanks to the developer for having the vision to actually put up those buildings. Those were not small buildings; they were quite large buildings. And it's only through research like that you can really bring in the information that you need to, you know, go forward. I'd like to open this up. We have three panelists that I'd like to invite to turn on and join us. And I'd like to ask them one by one. George Rodriguez Alvarez to come on. He is the associate professor at the University of Coruna, course consultant, Architectural Association. George has a PhD architect specialized in sustainable design and urbanism. He has taught in the Sustainable Environmental Design program at the Architectural Association and has taught at the School of Architecture in London at the AA since 2008 and at the Urban Planning Department at the University of Coruna, Spain since 2010. He has been a guest lecturer and postgraduate programs such as a Master at Collective Housing and the Master in City Science at the Polytechnic University of Madrid and Master of Bioclimatic Architecture at the Isthmus University of Panama and Master in Renewable Energy and Sustainability of the University of Santiago. His research on energy and urban design was awarded with the Reboot Research Trust Award in 2015 and the Best Paper Award at the 32nd International Conference on Passive and Low Energy Architecture. Welcome, George.
Welcome. Thank you, Silvio. Thank you so much.
I'd like to also introduce John Peterson, who's a highly accomplished architect with over 30 years of experience, believing that an architect should provide intelligent design solutions that make sense in a world where climate change is the preeminent problem. He has developed a reputation for successfully designing and managing challenging, award-winning sustainable projects. Currently, John is a senior associate with SVN Architects and Planners and is involved in detailing regenerative design processes that use to address SVN's social environmental commitments. As Thomas mentioned, John Peterson was the project manager for the Manitoba Hydro project while he was at KPMB. Welcome, John.
Thank you, Silvio. Thanks, Thomas.
And third, Blake Jackson is an architect working at the nexus of sustainability, wellness, resiliency, and equity, who serves as the Global Director of Sustainability for NORR. Blake has 23 years experience in the AEC industry, holding a Bachelor of Architecture degree from Canisius State University in Marietta, Georgia, and a Master of Architecture and Sustainability Environmental Design from the Architectural Association Graduate School in London. Blake is a prolific author, speaker, and educator in topics affecting the built environment. He currently serves on the advisory board of the University of Massachusetts Dartmouth's Interior Design Program, and from 2016 to 2018, he was elected to the board of the Boston Society of Architects as their Vice President of Advocacy. In 2015, Blake was recognized by the Building Design and Construction magazine as the top 40 under 40. Welcome, Blake, to this session.
Thank you very much for having me, Silvio.
So we're going to start off, and I'm going to ask each of you with your initial thoughts on very inspirational presentation by Thomas. And I'm going to start in Spain with George.
Hello. Yeah, as you said, it was a very instructive, inspirational presentation by Thomas, and I would like to emphasize three aspects that I find particularly interesting and that I can extract and they can generate, I think, a very fruitful discussion. The first idea that I think was transparent throughout the presentation is that environmental design, there is no doubt it helps generating not only good, nice and appealing architecture, but also healthy environments. So it's not an addition, it's not something in a checklist, but is intelligent strategies such as the ones he showed us in the Manitoba building, for instance, are at the core of the architectural concept as well. So this integration, I think there is a great lesson that as he suggested, is very difficult then to imitate. And sometimes when these buildings are so good in terms of performance, the imitations perhaps sometimes stop at the superficial because they involve such a highly skilled knowledge and careful design that is very difficult to replicate. And then it becomes very important. The second idea that I think emerged from the presentation is the buildings, the lessons and the insights we can extract from building precedents. This idea of looking at the simplicity, having simplicity as a goal, I think that's a great idea because there is many things that we can learn from precedents, from old and traditional buildings, starting with this initial image of the flat iron and the design of the windows. We could also look at the Victorian window, and an element that was tested over decades and centuries, and with very simple design responded to many different challenges, that of daylight, ventilation, that was essential in Victorian houses, the views, the connection with the outer environment, the proportions, the vertical proportion, also having to do with the structural performance of the walls. And the third idea is that we can learn from existing buildings, but not only from that, we can also learn and should learn from the users. And that idea of reconsidering comfort and the insights that we obtain when we actually not necessarily ask the user, but we observe the users, how they perform, their behavior. And very often we see that, well, in simple terms, they tend to tolerate much more than we think. I think combining these three ideas would be essential to have this critical reflection on the field and on the profession as a whole.
Do you have any comments, Thomas, to the initial thoughts?
Let's say, very good summarized my entire presentation. Thank you for that. I think there's not much more to add.
Okay, so let's go on to John. Your initial comments.
Great, thanks, Silvio. Yeah. So Thomas, you invited me here today to do a little bit of a trashing on Manitoba Hydro. So it's fine. It's okay. It's okay.
I didn't trash it.
No,
actually,
I
the
know.
opposite.
Yeah, I know. But some of the overall concepts that we were deep into those long charrettes, charrette phase that we were trying to integrate as much as we could into the project, and a couple of things that kind of came to mind, I think, just as you were speaking and kind of evolving your thoughts about comfort, really came down to how Transsolar played a key role in the design of the overall systems in the building, in the sense that you're always able to demonstrate to the design team and to the client a predictive sense of comfort and an actual kind of I guess a proof of concept that something was going to work. Because I think there was some thoughts in the original days when we were talking about, it's so cold outside, is this double facade going to work? Well, we know the south atrium can work, but is the double facade? So there was lots of safety pieces that we put into it, like radiant heating and cooling into the double facade, just to trim up the temperature. Now, I think how Transsolar kind of works in terms of designing for and predicting those sense of comfort is not the common kind of tool set that a mechanical engineer might carry into a design concept. How do you see kind of like that role of kind of more democratizing or making more common the tools that you use to predict that comfort? Or do you think that you can move into a more prescriptive sense and saying, if you do this, it's going to work? We don't have to prove it anymore.
I mean, but first of all, I think it's very important for me. I don't want to trash the building again. It's I'm super proud of this building, and I'm so happy that I could be, and that we at Transsolar. I mean, it's not just me. I mean, it was Alex was very important. Like there were these few people from our side, and many more people were really important to MakerStream, etc. I think we could name many people to achieve this. And we were sitting together over a beer in Toronto. I'm not sure if you remember when we started to discuss why this hasn't taken off in Canada, even though the building has been considered a success. And this is actually, you guys made me think, did it fail as a role model? So if we believe we develop a role model. So, and the building was intentionally we wanted not only to have a signature building, the intention was always that this should become a role model. Manitoba Hydro were setting up a website where they published all the results to make people try or encourage people to copy, not the building, but the main thinking of this climate adaptive or climate responsive approach, of this adaptive facade systems, etc., etc. And that's something which did not happen. And that made me think. And on top of this, this problem of monitoring and performance gap, and that it takes too long to get our buildings to work as designed, which is, let's say, not us, let's say the whole industry in general. Our buildings are too complicated. So those are the two things which were driving it. Now coming back to the question of tools and using tools in design. I mean, we live in an age. I mean, Theodor Fischer, who designed the school in Munich, in the Heimhauserstraße, I think someone asked, and after the name of the school, I actually don't even know the name of the school. I don't know the place. It's in the Heimhauserstraße in Munich. Theodor Fischer, architect. At that time, there was common sense. Designers knew what they need to design to create the best, to make the best out of the situation. We live in a time where you have to put numbers to it. It has also to do with responsibility. Like if you bring innovation to design, there's always a risk, and the client says, okay, who takes responsibility for this risk? So you have to go through the modeling. Basically, I said, like, if people would believe me, we wouldn't need to go through all the modeling. So that's what you said about prescriptive. No, I think the modeling, that's a result of our times. I think that's what we need. But is the modeling, are the tools most important? Or isn't it more important? Like, the tools do not provide good design. I was at a conference in New York where everybody presented the latest tools they have developed. And at Transsolar, we are part of this circle. We are part of the game developing tools. And I said, aren't those tools all meaningless if we continue to build the same bullshit? Sorry to be so blunt. So if we don't see better buildings, what are the tools about? And so I think it's more important that we rethink aesthetics, that we rethink design, architecture, and then the tools to support this innovation towards new simplicity, they will come. I mean, there are now so many skilled, like even the kids at our university, they're sometimes so skilled in using these tools, but they don't know what the numbers mean. They don't know how to use it. And so as a profession, I think we have to give the direction, and then there will be people and tools and skill set to support the direction.
Thank you, John. Blake, your initial comments?
All right, I have many. So first off, I just want to say thank you for the presentation. There were a lot of very interesting insights. I'll try not to double everything that my colleagues have just said here. I'll second just how important the commissioning is. I think it's something that I've spent a lot more time in the last year or so trying to sell those services and talk about the importance of it, not to sell the services, but just how important it is as part of sealing the gap between, as that you pointed out in your presentation so thoroughly, between the intended performance and the actual. And even the most sustainable buildings that are built tend to be a bit too complicated. I mean, I was recently in I was in Liverpool last week, and I hate to admit this for recording, but I'll do it. I was in a smart building where I got trapped in the elevator. And after I saw the second staff member that I had made friends with because I had been on the elevator for that long, he finally asked me if I needed help to get out. And I said, please. And he said, oh, what are you, we started talking. He said, oh, what are you here for? And I didn't want to tell him I was an architect trapped in an elevator. I said, oh, I'm a medical doctor. And we had a big laugh and we went on. But I agree that buildings are too complex. And I think that, one of the things that resonated with me with your presentation is that, and you just summarized it a second ago, is that we live in a time when common sense is optional. So, with regard to going back to that, you rooted these projects in a thorough understanding of climate. And once you do that, if you're working in the same place, I think it's hard for international practitioners now to work in the same place in the way that perhaps Antonio Gaudi did with Barcelona and the areas around. But Once you do that analysis, now you're equipped to hit the ground running on the next project in Winnipeg or anywhere nearby there without having to redo the analysis. So I think it's important for us to remember to root our work in climate. And I love the idea that it generated not a stale architecture, but one that was about the place. And I think that there can come beauty from an understanding of the place. For example, on Manitoba Hydro, it's against conventional wisdom to orient buildings the way that you had to by virtue of the site. Yet you were able to turn that what would be considered a poor orientation into a strategy for success. And so that in and of itself generates a lot of creativity that I think a lot of architects and engineers aren't thinking about the challenges of a site, particularly when we're hermetically sealing buildings. One other thought that came up that I'm glad that you bring up is the ability to scale these initiatives, particularly with the thermal mass walls, into a more hyper-dense urban environment, which we tend to be more practicing within. I was intrigued by this idea just because we're trying to balance a reduction in embodied carbon as well as a reduction in operational carbon in buildings. And when you start utilizing passive house, which has become not very, but much more common in North America than it was, say 10 years ago, you start to see a loss of area. So we did a study for a 15,500 square foot floor plate for a typical multifamily residential building a few years ago. And we learned that because of the loss of square footage in the building, we were losing approximately half a studio apartment per floor. And we generally build 30-level towers in and around the Boston metropolitan area where I was practicing at the time. So that's 15 units in a time that makes the units at a per unit basis more expensive to build per unit. It's working against our efforts, right? So it's part of the reason why we should make buildings more simple, and also to realize the fact that space is a premium, particularly in cities where we have affordability crises, housing crises, and a climate crisis. Two final thoughts, not to take the stage, but there were a couple of controversial items that I would like to bring up to maybe have you expound upon. First off is this idea of putting people into discomfort. I like the idea. It goes against complete conventional wisdom that has been set up in BREEAM and with ASHRAE and LEED in the United States, and even the well building standard. They tend to focus on steady states measurable by ASHRAE 55, which is our international thermal comfort code. So I'm curious to see how you're going to tackle taking that on because it's so ingrained in the practice. Secondly, the window to wall ratios at below 30% is controversial. The feedback that we get from occupants of passive houses is that they love it. It's warm when it's supposed to be warm. It's cool when it's supposed to be cool. And particularly in cities, the noise is reduced to an acceptable level because we're starting to build housing next to places where housing historically hasn't been good to place it. So passive house is a means by which we can mitigate many of these strategies. Their biggest complaint, though, is that the windows are too small and they would like a bigger view. And obviously, we have to balance these things out, but it was provocative for me to see a 20% window to wall ratio in a building. And I'm curious your thoughts about how do we balance those psychological expectations for bigger views and more daylight versus what is acceptable in terms of actual illumination and actual comfort.
Okay, so first of all, your point about commissioning, I think many of us are also talking to politicians and talking to people who are in governance, etc. And we always say, why don't you make commissioning mandatory? Commissioning and monitoring. Why don't you force people to prove that their energy, that their actual energy consumption is what they have predicted in design or projected in design? So that would be so easy to solve, but everybody is hesitant. But let's say it's a problem in housing, but it's a bigger problem in commercial buildings. There's a study in Germany showing that modern commercial buildings do have an average performance gap they looked at of 70%, 70. That is just unacceptable, I have to say. And we have to do something about it. So that's this point. The loss of square foot, would be so easy to solve with zoning bylaws. I heard, I'm not 100% sure if it's true, but I'm pretty sure it's true because the architect who told me, he worked in Zurich, and he said in Zurich, the external wall in the zoning bylaw, would, like when you hand in your application for building permit, the outer wall is just a line, no matter how thick it is. So it would be so easy to solve this question of thick walls by just changing the zoning bylaws from cross to net. And to be honest, Canary Wharf, when we look at Canary Wharf and we think about why do they build only all glass buildings, not with a double facade, with a single layer facade, the reason is that the glass facade is the thinnest facade we can build. So based on given zoning bylaws, it's the most amount of square foot we get out of a property. This is driving the design. Someone recently in a discussion said, I really like this. It's not the architects who design buildings, it's the planners. The planners design building. And there is a truth in it. And we need to better understand this implication of zoning bylaws. Okay, and then discomfort. I mean, this will be like a long battle. This is not going to be solved within a year. And it's not only us, fortunately, believing this and working in this. I mean, UC Berkeley, Gail Bragger, etc., all these people, Australia. There's so many institutions worldwide who now work with biosignals with the same idea, dynamic conditions. Do we get a better understanding of dynamic conditions? Do we get a better understanding of temporal discomfort? I think the point is time, it's temporal. There's no code, it's always steady state, as you mentioned. And so we have code conditions which are based on steady state because that's what we understand, but we never studied dynamic conditions and what comfort and discomfort means in dynamic conditions. And I really believe, due to the amount of research institutions now working in this field, that we are capable to get to a level of knowledge. We would never be capable to get to a know-how by ourselves. But all these institutions together within, I mean, it's probably going to take 5 years at least to gain the knowledge to be convinced enough that we can implement it into ASHRAE, for instance, like they achieved it with the adaptive comfort standards. So at least 5 years until we can talk to ASHRAE, let's put it this way. So it's going to be a long run, but a very important one, because I'm really convinced that steady state is not healthy. The problem with health, so we have people from medicine involved in this research. The problem of health is, let's say, to get a scientific confirmation or a scientific proof of what is healthy and unhealthy is very difficult, because you need a lot of data. And they said, like, they know, for instance, there's Finland, and the Finns, they all have a sauna, and there is Norway where they don't have all saunas. So sauna bathing is very common in Finland. So now they can compare similar climate conditions, similar light, daylight exposure, etc. They can compare big populations with both cases, and there they can get a scientific proof that sauna bathing seems to have a positive impact on health. By the way, it's also about discomfort. So you bring your body out of comfort for a certain period of time. And so we try to find other methods to get a proof, because we're never going to get this amount of statistical data we need to really get a proof of concept. So we try, anyway, we try to compare it to other fields. So different methodologies, and it's really interesting to work in interdisciplinary teams about this. But it's going to be a long run. And then the last thing, that's the most interesting one. We really got used to this class. And when we work on projects and tell people to reduce, or we discuss in the team, a reduction of fenestration ratio, it's the people come in who sell the apartments, for instance, their first reaction is no way. The market expects, look at condos in Toronto. This is what the market expects. And how do we get out of it? First of all, do they really know what the market really expects? And the second question is, I mean, the 20% fenestration ratio, we wanted to go to the bare minimum so that we don't need shading, that we get good thermal comfort without shading devices. And I mean, this was a research project. Would I design it for myself with the same fenestration ratio? Probably not everywhere. I mean, it would be also nice to have like a balcony with a sliding door and a bigger window. So even for myself, but this was particularly a research project. And what we see, like when there was no complaint, I said, like we went through questionnaires. People complained about many things, but there was no complaint about the fenestration ratio in this project from all the people we asked, and we asked everybody in these 23 apartments we have in those 3 buildings. And I think the reason is, and this is now just speculation, the reason is the floor to ceiling height. Having these almost 11 feet floor to ceiling height and these tall windows makes these windows are pretty big. Such a window has more than 2 square meters, so more than 20 square feet. It's big windows, but the wall is even much bigger. But I don't know if, let's say, height, I always said height matters, but it's all speculation. Pure speculation.
Hey, Thomas, and in regards to the your work where you've kind of unearthed that little thing on the biological clock and its impact in terms of people's comfort, it reminded me there's a book by Daniel Pink on the biological clock, and the secrets of being able to make decisions at particular moments. It's the book's called When. But do you see the kind of that kind of a highlighting of I guess comfort at particular moments in the day? Do you see that as being quite readily brought into kind of PMVs and the idea of comfort being expanded to suit that?
I have the feeling that we are the first ones tackling this, actually. And the Fanger studies in the 70s, and even the database, like there's a database had been built around UC Berkeley and the Center of Built Environment about comfort. It's the biggest comfort database with test subjects and etc. That exists worldwide. There is no, in the database is no time when they did the tests. So it was always ignored what period of day those tests had been made. We just don't know it. But I think we have done now, we've conducted something like 5 to 10 studies. And in all studies, we see the same pattern. We always see this over and over again. It's a difference, it's a big difference in the morning and in the afternoon. And then there was one, even to the extent there was one student who came and said, can I start later? Because usually we do 8 to the noon and then from 1 to 5, those 2 times 4 hour shifts. And she said, like, I usually get up later. Can I start later? And so then we shifted her 2 times 4 hour shift to later times. I think she started at 11. And the funny thing was, didn't matter. We see the same pattern. For her, the morning starts later. So it's not about actual time. It's like subjective biological time. What's your biological time? What's the morning for you and what's the afternoon for you? That was quite interesting. However, I think we don't have the answer yet. It's also a bit counterintuitive of what we wanted, or let's say against what we wanted, because we always have lower temperatures if we use nighttime cooling, or in Manitoba Hydro, the slab cooling, we cool it at nighttime. So you come in the morning, you have low temperatures in the morning, and then you want the building to allow to become warmer over the course of the day. And so you have the highest temperature when the body is creating the biggest heat stress. So it was not a result we were happy about. And we don't know how the answer yet. So the other question we ask, but would it be healthy to cool then in the afternoon, to work with a mechanical system against your biorhythm? So maybe it's actually healthy that people have heat stress in the afternoon. There must be a reason why, when the body is creating more heat stress in the afternoon, maybe it's unhealthy to work against it. But it's all like with each study we are doing, we come up with a new hypothesis and no answer. So this is where we are, basically. But definitely, I think employers should take it into account. Like even we at Transsolar are not able to manage, but we should think about how we work. How do people like having, I think it's much more productive having people doing concentrated work in the morning. So you should have people not watching their emails in the morning. No video conferences in the morning. Everything happens in the afternoon. I think that's would be something easy to react to this. Or reducing our work time to 50%. That would be the other conclusion.
Yeah, that was my thought when you were showing this, that perhaps would be the best idea to not do any work at all after lunch, because I think most of us will feel like our metabolism is focused on other things. And don't you think that perhaps some of these insights that you are obtaining through this research and like the one of the expanded comfort band, or this on the metabolic biorhythms, that is going to be hard to provide this evidence, but perhaps the hardest part is to implement what it involves huge cultural shifts, perhaps. Like if we have this information and we have this evidence that doing work is much harder after lunch, and to run our buildings, it's much more costly. So perhaps the idea is to concentrate the work in the morning. And now in Spain, we are now debating about the number of hours that we work per week. And so it's getting very, very, very difficult to just move a single hour per week. 1 year ago, we have a strong discussion on comfort due to the energy crisis derived mainly from the war in Ukraine, and because the energy costs were so high that the government imposed a maximum limit that was, well, mostly 1 degree below the current threshold. So there were huge discussions that people wouldn't tolerate just this little variation. And so that's why my question would be, do you think that the research is revealing such important implications that the implementation is going to be a real challenge?
I think we certainly need to have, first of all, more research and a debate in the scientific world, and also a debate within, let's say, the professionals, under the professionals. I think that's very important, so that we become more sensible about this question of comfort and the edge of discomfort, and what is our design goal. And what you mentioned about working hours, we have the same debate in Germany, and they talk about working only 4 days a week. I would find it much more productive to say, let's work only 6 hours per day, but 5 days a week, than working only, because like you can extend the morning a little bit. That would be, and I think would be more healthy for people, more productive for the company, et cetera, than having people working only 4 days a week. That would be my suggestion as a result. But in terms of implementation, I think what we can all do and what we have to do, again, is become more sensitive about the question of comfort. And when I come to North America, and not only North America, I mean, also Asia, Europe is better to that regard. I mean, in Europe, we are used to have wider temperature bands, comfort bands between winter and summer, and also over the course of the day. But internationally and in North America, the comfort band is very narrow. And I mean, typically women, and I know when I say this in North America, people say, Thomas, be careful, gender, etc. But it's scientifically proven that women perceive comfort differently than men. Women are used to bring their sweaters to work in summer because it's too cold. Come on. And that's just stupid. Like we design, let's say we stay within PMV plus minus 0.5, but we design and run and operate buildings at minus 0.5. So with 10% of people feeling dissatisfied in steady state conditions. We could also operate it at plus 0.5. So instead of having 23 degrees, having 25 or 26, having also 10% of the people being dissatisfied. So we have the same percentage of people dissatisfied. We stay within ASHRAE 585, we stay within code, just we tackle towards another group of people that feels dissatisfied than what we had before. So this would be so easy to implement, so easy for everybody to understand. But I think it's not going to happen. Like we worked for a couple of years ago, we worked on a design for one of the big tech companies from California. I don't want to say the name. I signed an NDA, but we were shocked. So it was in the US. They said, we talked about comfort, we talked about variation of comfort, we talked about mid-door, so have spaces that, like the winter gardens at Manitoba Hydro, have a bigger range of temperatures, and that people could choose their ideal climate. And they said, like, just provide 74 degrees. That's a 72 in winter, 74 in summer. That's what we want. Just provide that. And we got from their sustainability group in advance, we got the sustainability guidelines, and they were the sustainability guidelines. They were like super innovative, with a pretty big temperature band over the course of the year. But then when you are in actual design and you deal with the people who are responsible for actual design, they don't care about their sustainability guidelines. So I thought we should encourage women in North America or worldwide to start a campaign, calling it #NotMyClimate or something like this. Then things might change.
Thomas, I had a question for you about fresh air, and we tend to do a lot of institutional work, and people talk about 100% fresh air and all the mechanics that goes into doing that. And certainly in Toronto and in a lot of the big cities, commercial and institutional, and a lot of these buildings, I mean, Manitoba Hydro was what, 14 years ago now? It's a long time ago, and it should have been a model, and not to go back to it, but it's very unfortunate. And yet we still see today commercial and institutional having a lot of difficulties when you bring up operable windows in higher rise, operable windows in even a lot of residential buildings in Toronto. There's a resistance to it. You mentioned New York City. My daughter lives in New York City, and it's amazing that you still, in this day and age, don't have operable windows where people can simply open a window and get fresh air. And there's a lot of reasons from a development side as to why they refuse to do that. But do you have any thoughts on that? I mean, it's really tough a lot of times on projects to continue to fight the developers, but it's something in this day and age that shouldn't be happening.
I mean, I can only agree to this, what you said. Like, I find it even inhumane having no, it's a torture having no operable windows. It's just against humans. Humans sometimes want to connect with the outdoor environment, and they have to connect. We know, for instance, that daylight, people need a doses of daylight per day for vitamin D and certain hormones, etc., etc. You get this doses if you're outside for 1 hour a day. You certainly also get it when you live in, let's say, proximity of a window you can open. The same with microbiomes. People need exposure to microbiomes. You get this from outside air if you open a window. Then the third thing is I forgot what I wanted to say. Yeah, now I'm back. We measure CO2 in buildings in terms of air quality, but the concentration, CO2 concentration we have in indoor environments are basically irrelevant for humans, for people. We measure it because we believe that there is a correlation to VOCs and odors. First of all, why don't we design indoor environments with low VOC emissions, natural materials, no glues, all of these kind of things? Why are we not more careful about the furniture? I think VOCs is a problem. We don't get it down to zero, but we did measurements in buildings like the Alnatura building I showed, where the total VOC concentration is 1/10 of the threshold based on the German sustainability building rating, 1/10. And only because everybody took care about what kind of painting, what kind of materials, no glues, what kind of furniture, all these kind of things. It was not rocket science, just being more careful. So that's number one. We have to minimize VOC, total VOC emissions. But then what we as humans perceive as stagnant, bad air quality are odors. And we believe that there is a correlation between CO2 and odors. It's just not true. And we don't have sensors to measure odors. Of course, there are people who say there are measurements. I have not seen any scientific proof yet, but that they know better what's a good air quality and what's not a good air quality. And when I go in a lecture hall, for instance, at our university in Munich, and it had been packed with students before, and it has a mechanical ventilation system, which is CO2 controlled. I walk in and it's smelly, it's stagnant, it's smelly, it's bad air. I know the CO2 concentration is absolutely right. And I hate that I can't open a window in this 15-minute break to refresh the space. So that's why I say it's a torture not to allow people to follow their own intuition. And their intuition is right. It's correct. It has a reason. So I think we shouldn't do this anymore. And John, I think you certainly confirm that the biggest compliments we got from the users of Manitoba Hydro was not thermal comfort, was not even daylight. For daylight, it was even difficult. They complained about glare and too much light, etc. Some of them, sometimes. But everybody always said, what an air quality in this building. Because we had no recirculating system. We provided 100% outside air and these operable windows. And during COVID, they loved it. They loved their operable windows. I think that's the message we should take and say, like, give people out 100% outside air. Let's give up with these recirculating air systems wherever possible. I mean, if you are certain building typologies where you don't get away from recirculating air, but in housing and in office buildings, we shouldn't have recirculating air systems, and give people operable windows.
On that note, and I agree with that, right? Give them operable windows. How do we eliminate, because I think one of the challenges working against us, other than insurance companies that limit the opening for windows to 4 inches or less, which makes it very difficult to passively ventilate, particularly deep floor plates, but even smaller spaces as well. How do you communicate when and how the user should interface with the systems? I think a lot of times we get, forced by clients to design systems that are foolproof, fail safes, that it lends us towards the hermetically sealed environments whenever we're trying to control everything to such a level, right? And so on a building like that, a large commercial building, it's easier in a residential building because people can navigate their own comfort, and also they're responsible for failures if it results, like a frozen pipe or something like that. But in a commercial building where there's a lot more users and they're transient by nature, how do you communicate to them how to properly use the building? How do you engage with them in a long-term pattern to make sure that they continue to use the buildings properly? And are there technologies, or are there low technologies that you utilize to do that?
I mean, we had the Manitoba Hydro, we had long debates about this. I mean, there was always this idea to have a green and a red LED on the windows, like indicating when it's a good time to open, when it's a bad time to open, these kind of things. At the end of the day, we didn't install anything, so we relied on people. And there was like a discussion because like when the conditions in the facade cavities are fine, like conditions in terms of temperature and humidity, we shut off the mechanical ventilation entirely, and then the entire tower is relying on people opening the windows for providing fresh air. And like measured in our monitoring, Manitoba Hydro published that a third of the year in this very extreme climate of Winnipeg, we operate this building without any mechanical ventilation. A third of the time, just relying on people. And so we ended up with a very simple system saying, through the intranet, they get a note, the building is in natural ventilation mode, and it's up to the people to open the window. I think first of all, I think we need to be aware that user interaction in commercial buildings does not have the same level of impact than it has in residential buildings. The performance gap in commercial buildings we see is mainly dependent on failures of the BMS, number one, like the building management system, and then hydronics. So it's always related to controls and mechanicals, not so much as a result of people opening the window at times when they shouldn't. I'm a bit tired, or I find the term low-tech and high-tech always a bit difficult because there is no definition. Even those 3 einfach bauen buildings, I mean, the materials they use, this insulating concrete, I mean, this is a super high-tech product. The same for these insulating bricks. So what is high-tech? What is high-tech? What is low-tech? Triple pane windows hinged in the middle. I mean, those are high-tech windows. So that's why we like the term robustness. We haven't managed that this term made it into the profession, but the idea of robustness is, and you can describe it with a methodology, and you can put a number to it. Basically, the idea is that you design a system so that, let's say, what we call uncertain boundary conditions, very engineering term, which could be people. People are uncertain boundary conditions. Could also be a mechanical system that doesn't work as designed. Climate is a very uncertain boundary condition. That those uncertain boundary conditions does not have a big impact on the result. That's the idea of robustness. And so you can define the uncertainties and put it in your model and see how your system, how the performance of the whole building reacts to it. And that's what we liked. And that's something which is used, robust optimization is the methodology, how it's called. It's used in the automotive industry. It's used in all industries. It's not used in the building industry, which is kind of ridiculous because we do have the biggest uncertain boundary conditions. So the point I want to make is, I know you're absolutely right. The user, particularly in housing, but also in office buildings, do have an impact on how the building works, etc., on the building performance. But we see so much change of people that we think that being constantly engaged in educating the people does not help. Putting together a manual, we do this for every building, but we know that nobody's looking into it. I never read manuals. Nobody reads manuals. So I think it has to be intuitive and it has to be robust, what we design. I know that this is not a satisfying answer, but the best answer I can have.
Thank you, Blake. I'm going to move to Tobias Fellows, if you can come on, please. Tobias Fellows is the principal with NORR in our Ottawa office, and he is going to share some of the questions from the audience. Tobias.
Hi, Thomas, and everyone on the panel. It was a great presentation and great discussion afterwards. I've listened to your presentation previously, Thomas, on the Manitoba project, and I've always struck by how you kind of take things back to first principles, and you're looking at things at a very base level, and I think that's really an interesting aspect about your work. We have a question that David Cluzio asked in the chat, and I'll just go through that now. Very interesting talk, provocative for a company that I think is at the cutting edge of complex, high tech. It is interesting to hear you revisiting this. I have a couple questions regarding the 3 test buildings. What were the cladding systems for each? Also, did you have any prescribed insulative requirements that you had to meet in order to allow you to build the project? So I guess this is kind of a code question related to the building bylaws, and to get to your point around the planning bylaws designing the building. So did you have any insulation requirements that you had to meet that caused issues when you were designing and building those buildings? Yeah.
Let's say first of all, Tobias, thank you very much for your comment. Highly appreciate it. And then second, I'm not sure if we it was always our DNA of Transsolar to design low-tech buildings, to integrate passive design, passive strategies into buildings. We did not understand enough, or we always had this aim to combine it with, let's say, complex facades. I think this is what probably changes the point that we are more and more convinced that, first of all, everybody talks about cement and concrete in terms of embodied carbon. Nobody talks about embodied carbon in glass, which is like outrageous if you go into the numbers. I calculated the Manitoba Hydro double facade embodied carbon of 1 square meter. It's more than a 25 centimeter concrete wall with 20 centimeter of styrofoam insulation. It's about twice the embodied carbon. Nobody's talking about embodied carbon and glass. That's something we should also take into account. So it's more this aspect of the question of these highly complex facade strategies we followed, if this is really a successful approach. In terms of systems, we always believed in low tech in terms of mechanical systems. So this did not change any much. Then coming to this question of cladding, there is no cladding. It's a monolithic wall. One is insulating brick, one is insulating concrete, one is timber, mass timber. And concrete is finished. Then just with pouring concrete, you take the formwork off and you're done. The timber needs a weather protection, which is also timber, but you need a weather protection for the timber. The masonry, the brick building has a plaster, just a plaster. So no additional cladding system. We have a code requirement for in terms of U value, which is 0.28 watts per square meter Kelvin. Now I'm struggling because I can't translate this into BTU per square foot and degree Fahrenheit, and I can't translate it into R value. But it's a pretty high requirement. That's why the insulating concrete wall is 55 centimeters. It's almost 2 feet. The insulating brick is 42 centimeters, so 1.5 foot. And the timber is the thinnest with about a foot. But it's also a special kind of way of how they assemble this mass timber, that they have air gaps in between to improve the insulation, the U values. So we stayed within the code requirement of that time. It now increased in the meantime since we finished this building, but at that time it was 0.28. So if someone can translate it into North American units, maybe the person can write it into the chat.
Yeah, we'll see if we can get someone to take a look at that and provide it in the chat. Yeah, and so that there was a kind of a follow-up question around that insulated concrete. Exactly, that this is not a material we're familiar with in North America. Maybe you can just expand on that a little bit.
I mean, it's a fantastic material. To be honest, we love it. However, we have to say it was the most expensive building. It's still R&D. Like they put this kind of bubbles for insulation mixed into the concrete, makes the concrete very porous. And we were amazed because concrete does not have much absorption of humidity, or doesn't provide a lot of humidity control. But we were amazed how good the humidity control became with this very porous kind of concrete. It's so porous that with a hammer, you can put hammer a nail into the wall. But at the same time, if you have the edge of a window and a craftsman touches it with whatever, it's gone, it's broken. If you hammer onto an edge, it's gone. We had lots of difficulties, cracks, etc., etc. There's not sure if people know Schleich-Bergemann engineers. They have an office. They're also from Stuttgart. They have an office in New York and a few other places. Mike Schleich from Schleich-Bergemann. He's at the university in Berlin, at the Technical University in Berlin. He does a lot of research into this insulating concrete. It's called, in German, it's called infraleicht concrete. So infralight concrete. They don't like this term, insulating concrete. Anyway, he said like we are crazy that we built 3 stories without reinforcement. He said like we really wanted to test it, and we had issues with cracks. So make the long story short, it's a very interesting building. It's very uncommon here as well. It's very expensive. A few companies to have a patent on it. It's fairly expensive. The beauty is you pour it and you're done. No plaster, no nothing. Like it's exposed to the outside, it's exposed to the inside, but it's still R&D.
Very interesting. I'll sneak in a couple questions myself here, and you know, I think with regards to the Manitoba Hydro building, I think there, you know, architectural timelines are long. So I think there are a lot of architects out there that do recognize that as a leading business, leading example of something to try and attain. I don't think it's having tried to implement double wall systems on projects. It's not a easy to get clients to think about those things, and but I think that your project was definitely something very interesting. What I'm just wondering, was part of the rationale behind convincing the client, was there a financial model that had to be demonstrated the value back to Manitoba Hydro, or was it they were just really willing partners that wanted to push environmental design, or was there kind of a payback analysis that was done?
John, do you want to answer?
Sure, I can try to tackle that one. Manitoba Hydro's part of the mission statement was they were given the mandate for meeting, I think it was a 70% savings over a model national energy code building, and we weren't entirely sure how we were going to get there. But I think that the key piece that we always carried with the client group going through was the fact that there was 3 models always in place. There was the design model, there was the energy model, and then there was the financial model. And they always carried those things through at every decision. So I believe they had a 20-year payback as a minimum in terms of most of the systems. And I think in terms of the double facade, the numbers worked out for that. But when you came to some of the pieces on the south facade, we switched over to a triple glazed assembly. And I know the client group after the fact regretted that, because that was the point of the building that had the most complaints, the hardest to control, and the least performance. So double facade in terms of the post reaction from the client was that was the best thing to do, wrap it around the entire building.
But I have to say, like, we were constantly going through budget issues and value engineering. And I mean, particularly you guys, John, KPMB, I mean, it was like a hard time, let's say, going in cycles because of value engineering. What they did, what helped in the financial model significantly at a certain point in time, there was a study which is published on the US GDC website, and I'm sure it's still there. It's called sometimes like something like the benefit of green buildings or so. And they showed improvements in terms of productivity of green buildings. And so they used a very conservative number of this. That's why they also monitor sick days, for instance, to get proof of concept. And that helped with the financial model.
And with that, I'm going to have to stop, and I want to leave Manitoba Hydro on a very high note, because I think there was an award, a recent award, and that it won and a few years ago. And Thomas, you were in that, and you actually look quite well in that video that I saw. But
okay, thank you very much.
But it is
I aged a bit, I think.
Just a little bit, but you know, it's still quite a landmark and a model for all architects, and certainly for Canada in the architectural world. I want to sincerely thank George for joining us from Spain and being part of this panel. Thank you very much.
Pleasure.
For your time. John, for being part of this panel, and your work on the famous building that we've been talking about, and being a support on this panel. And thank you.
Sylvia.
And Blake, as always, thank you for contributing to the panel.
Very welcome.
And Tobias. And Thomas, that was very inspiring presentation. I think you know, as usual, when we have presentations from Europe, and especially a company like yours, we're we're just enthralled with the research and the background that goes into everything that happens in Europe, which is contrary, I think, unfortunately, to what happens in North America. And want to wish you all the best and continue success and moving forward, and your frankness with what's happening in the industry. I think that all of certainly the architects and engineers and the students that were on this session will benefit from this, and this will, in a week from now, it'll be on NORR YouTube for the world to see. So Thomas, thank you very much for your time and your presentation.
Thank you. Thank you, everybody. Thank you for the invitation. I really enjoyed it.
Thank you. And for everyone else that's on the line, we'll see you next time. All the very best.